Hello, everybody. My name is Curtis Casados. The members of this team are Jordan Muncie, Stephen Lindquist, Omar Akalat, and Matthew Mott. Our project advisor was Dr. Don Tremont, and we want to thank everybody for joining us today for our poster session of our product Foldable. Um, about a year ago, we had an idea to take an iconic arcade game that is typically cost prohibitive, largely inexpensive, and bulky, and convert it into a household product. To do this, we needed to minimize the cost while maximizing the accessibility as well as the portability. Employing our engineering design, we were able to use simulation-based results to create custom hinges as well as custom ramp. Based on these results, we were able to meet our engineering metrics. Our engineering metrics include a total weight that is less than 30 pounds, which we were able to meet by selecting the proper materials that were both lightweight as well as strength effective. We also were able to meet, we also had the metrics of dimensions to that similar of a large briefcase, which we were able to meet, which we did while using our custom hinges as well as unique folding mechanisms, which Stephen Lindquist will talk about later on. We had a maximum runway holding weight of greater than 30 pounds, which Matthew Mott will describe in greater detail later on. We had a noise level constraint of less than 75 decibels, which we were able to meet using dampening materials on our runway as well as our game board. To give you an introduction to our terminology of the pieces, if you look at the top middle picture, you can see that the game board is the furthest one in the back, supported by the supporting straps. The ball return is on the right-hand side of the product, which simply returns the ball to the user. We have runway R1 closest to the user, and then runway R2 closest to the game board. You can also see the custom hinge as well as the RAM. And with that, I will hand it over to Stephen Lindquist.
All right, so moving to the top left, once we were settled on how we wanted to fold our product, we needed to put that into action. So there are two critical folding pivot points on our product, one being between our runway 2 and the game board, and the other being between runway 1 and runway 2. We solved the hinge between runway 2 and the game board by simply adding a bolt that it would pivot around. But the second hinge was much more difficult to tackle. We struggled to find something on the open market that would satisfy our needs of needing to rotate 180 degrees, as well as being lightweight and fitting within our budget of less than $5 per hinge. Our first prototype, we decided to build our own, or design our own hinges and have them 3D printed. Once we got a design we liked, we 3D printed them, put them on the prototype, and they worked really well, but we weren't happy with how bulky they were, and we were worried about the cost to manufacture them, as we were hoping to have them CNC'd out of aluminum in the future. So for the second prototype, we went back to the open market to find something that a hinge that would work, and we were able to find some that were small enough that would mount on the top of the side rails of our second prototype, and they fit in our budget of just at $5 a piece. And in order to make them fit and fold in flush when the game was in transportation mode, we needed to notch down into the tops of the side rails, and this proved to be time consuming and hard to do accurately. And even when the game was set up, it was, their hinges were still pretty sloppy. So we ditched that idea, went back to the idea of designing our own hinges, but for the prototype 3. And but this time around, we went with a 16 gauge stainless steel sheet metal. We decided with stainless steel because our game was meant to be played indoors and outdoors, and we could have them cut locally by a laser cutting company and molded to the shape that we need for a low cost. 16 gauge sheet metal is only about a 1/16 of an inch thick, so our concerns were with strength right away. So we did a bunch of FEA analyses and in different vulnerable positions, and found that this was going to fit our needs, and came with a average safety factor of 5.24. We searched around for a local manufacturer to have them made, and we were quoted at $4 a piece. by one local laser cutting company to have them cut and formed everything we would need. But unfortunately, we were unable to move forward with having them produced when the shelter in place was put into action. All right, go ahead, Jordan.
Yeah, so we had a lot of challenges with this. We basically wanted to take something that's the size of a large arcade game that's like 8 by 5 feet tall, and we wanted to fold it up into this little suitcase. So that hinge, which was a lot of Steven's project throughout this whole semester, was huge because we needed something that would allow it to collapse in. The next thing that we really needed to tackle was that there's a lot of components here that influence the playability of the actual game. So with our first prototype, we didn't worry too much about it. We knew that you'd have to throw a ball up the runway, it would have to hit a ramp, it would have to land on this game board. But the first thing that we noticed when we started doing this was that it wasn't a lot of fun to play. It certainly didn't feel like the game that we were trying to emulate. So we looked at the physics of the situation and realized that the ball throw is a factor of this ramp angle right here, the speed that the ball is traveling up, the distance between the edge of the ramp and the edge of this game board, and then the angle of the game board itself. So there's a lot of different factors going on here, and we knew that we wanted to model the arcade game itself, where the ball should, when it's thrown, hit and connect with the second pocket at roughly 90 degrees. So we knew that whatever we designed, all of the parameters had to result in a ball falling into that second pocket at roughly 90 degrees. In order to accomplish that, we took the physics, we boiled them down into the relevant equations, verifying our assumptions. We created a graphic user interface that would map everything for us in 2 dimensions as if we were kind of looking at a side angle of this actual system. And then we started just testing different parameters. We found that we were going to want a ramp presumably about 52 degrees with everything else set up the way that it is. We tested ramps at 45, 50, and 55 degrees, found that the 50 degree matched our model within 4.5%. So that was great for us. We slapped it on and tested it and found that it was much more fun to play, and it kind of got the result that we were aiming for to begin with. The next important piece for us was making sure that, we've got this, it's fun to play, but is this runway actually structurally sound? And I'm going to let Matt kind of take over and talk about the work that we did there.
Yeah. All right. So yeah, the runway is like the biggest part of our design. And so we realized after building our first prototype that it's also the heaviest and the weakest part of our design. So we realized we needed to optimize both its weight and its strength. So we began with simple like bending force calculations. We tested what it would be to put like a 20-kilogram child sitting in the middle of it. And we also tested impact force calculations of like a ball hitting it, like a heavy ski ball, impacting the center of the runway. And this helped us determine what material to use, what thickness to use, what dimensions were best. And then once we had like these dimensions kind of set, we built our second prototype. And then we took the base piece off this prototype and duplicated it and ran a displacement test on it. So we supported it on both sides. And we incremented weight in the middle of it by 5 pounds and then 10 pounds once we got to a certain weight. And we measured its displacement at each increment. And we did this until failure, until it broke. And then we modeled an FEA simulation off the same piece under the same conditions. And we incremented the weight on the middle of that. And that gave us results in the displacement and factor of safety and stress. And we got these displacement results and we compared them back to our actual test results, as you see in figure 6, the graph down there. And then with both these results, we created a line of best fit of our actual predicted values. And we also found where like the weakest points are in our runway and the strongest points were. And basically what we concluded is that the wood itself, even though it's thin, is actually plenty strong to hold what we expect to see like playment of this game. Because the side rails, especially on the ball return, basically make the whole piece like a big I-beam. So the wood itself is very strong. That actually led us to a bigger concern is the connection between the two pieces might be the weakest point. So our hinge in the middle is more of concern than the actual wood. And that'll lead us to Omar.
So starting with this project, we all went to play the original game to see how it feels and what is the dimensions and take reference dimensions of the original game. So we started off building the preliminary design using duct tape and cardboard to figure out like how it would look in reality and do something fast, and to figure out how it's gonna fold in a briefcase without any like extra edges or without any edges. So we created this cardboard design, and from here we started to design our hinges, as Stephen said. So we designed our own hinges. Uh, we created. We didn't focus much on the aesthetics in prototype one. All what we were like focusing on is just like how the folding mechanism and how it's gonna appear when it's folded, and how is the legs gonna work. So it turns out that we had like some good things and bad things in this design. Uh, we found that our hinges was working really good, as Stephen mentioned, but it was kind of bulky. The legs was really difficult to design. We did a lot of calculation to design these legs to create the 6-degree angle that we need for our runways so the ball can return. So in the next prototype, we tried to focus on all the problems that we made in prototype one and focus more on the aesthetics and how it's gonna look and appear. So the major things that we did was the ramp. We did a lot of calculation for the ramp and different angles. We tried different angles, and we made it. We attach it to the game instead of just like we didn't have the ramp in the first prototype. We would just attach it by ourselves because we didn't have room when folding the game. So that's the first thing. Second thing is the legs. We changed the design of the legs to have an angle instead of a straight legs, and we got rid of the middle legs. And we attach latches instead of the middle leg to support the runway, so it wouldn't like fold out. Second thing, we also reduced the thickness and the weight from prototype 1 to prototype 2 by half, almost everything by half. And we have one problem in prototype also. We had the hinge between game board and the runway. It wouldn't like support itself because like as you can see in the picture, like somebody was holding it because the hinge wouldn't support the game board. So we created this straps to hold the game board, and we did some testing, and also the straps allow us to change the angle of the game board for testing. We focused a lot in prototype 2 in the ergonomics and the aesthetics. Uh, uh, by ergonomics, we changed the height, the weight, and we attached them handles. So we were really happy in prototype 2, but in prototype 3, we tried focusing more in the aesthetics. So and the appearance of the game, so we can make it saleable. We changed the look of the ball return. We reduced all the thickness of the sides and rails from half an inch to quarter of an inch, and we did a lot of simulation to see if analysis to see if the quarter inch would support this weight. And due to the coronavirus, Jordan will talk about how it affected our prototype 3.
Yeah, so we're just going to catch up to kind of where we've come from this point. So we had prototype 2. Prototype, this cardboard was so we could just get a feel for the dimensions. The first prototype was so we could figure out how it's going to fold. And the second prototype was like, okay, now let's start making it fun. Let's start making it meet all of the metrics that we needed to meet. Once we had that, we realized that there was so much to improve on, which is kind of the theme of the last 2 semesters, honestly. When we wanted to tackle this, we thought it was going to be super simple. We thought it was going to be straightforward, definitely enough work for 2 semesters, but we didn't anticipate how much work it would actually be. A big piece of that came into the fact that there are so many components that have to integrate together. Just in this ball return, there's more than 20 individual pieces that all have to be dimensioned, and we all have to think about, we have to figure out how they fit together to start, and then we have to think about how they fit together when they fold. So anytime we want to change one thing, like let's say the height of this side rail, we have to change the height of the other rail, the height of the rail on the second piece, the height of the rail on the game board itself, and then that we have to adjust the location of all the hinges. So it's been a lot of work, but it's been something that we've been very passionate about. And this is a project that we care about not only within the concept of this class, which has been an excellent resource in order to kind of flesh out this design, but something that we're passionate about outside of this class, such that we want to finish it and we want to actually continue on and have it done by the end of this year. So the goal was for Design Day before coronavirus hit is that we were going to make not just one of what we wanted to improve on with prototype 3, we were going to make 2 of them. In fact, we had just started building 2 at a time when the shelter in place order struck. And we were going to have it, we've actually been designing the scoring system, which is going to go on this, which is the electronic component, which we'll talk about in our final report. But we had started designing that for Design Day such that what we'd be able to do is have one set up, one folded that people could hold. And we were going to have a scoreboard so that you could throw balls, record your score, put in your email address, and then we were actually going to give one of these away just to make Design Day kind of fun and interesting and to like really showcase what we had been able to accomplish with this. Now, coronavirus struck, so we've had to shift our focus away from building the 3rd prototype and actually finalizing this to reviewing our design decisions, working on the scoring system, getting that in place, and looking at different areas of FEA analysis such that we can feel more and more confident that when we finally can get around to building the 3rd prototype, it's going to succeed. So we are still planning on building that. We actually probably, as long as the shelter in place doesn't last forever, want to finish that up by the end of this year.